Welcome, everyone. I can't see you, but I'm sure you're all great. My name is Max, and today we are going to talk about Rust and Serverless and why they're doing such a perfect match. So can I change the slide? Yeah, cool. So who am I? My name is Maxime David. I used to be French, but now I moved to Canada about 10 years ago, so I'm a Canadian citizen. I'm doing Serverless at Datadog. I'm also an AWS community builder since 2021. If you don't know about this program, it's a great program led by AWS to share and to be part of a growing network of people passionate about technology and the AWS technology. I also started recently a YouTube channel. I have almost 600 followers, so definitely into the YouTube game. And I'm a big pizza lover, and this is really important for the demo, and you will see why in a moment. I'm also the creator of Lambda Perf, and we are going to talk about that in a moment. So yeah, without further ado, let's start. So first, I want this talk to be a bit interactive, and I want to show you the power of Serverless first. So if you can scan this QR code and order a fake pizza and stay on the page. So I'll leave you a couple of 10 seconds to make sure everyone can scan it. Let me know. I don't know how you can let me know, but yeah, I'll leave the QR code for 5 seconds just to make sure you have time to scan it. So if you scan it, you should be able to see this web page where you can order a pizza. So I'll go for a deluxe pizza, and I can see that my order has been placed. So this is a client side. When I order a pizza, I want to track the progress of my pizza. So now the order is placed. Let's see if we have some current order. Wow, this is really cool. Thank you so much for playing the game. So I can see a lot of different orders. So I will put the pizza in the baked state. So you should be able to see, as you can see, mine has just been baked. So you should be able to see the status change directly on your phone. And yeah, I'm not going to spend 10 minutes on that, but yeah, just to show you that with Serverless, and I will be back to the architecture in a bit, we can do some really cool stuff, such as like WebSocket. This is using WebSocket. And yeah, so we're creating a pizza. Then you have a manager interface when you can change the status. This will send a message over a WebSocket API, and the UI can respond to that event and display the status of the pizza. So yeah, this is all done in Rust, and we are going to talk about that in a moment. So I hope you're not waiting too long for receiving your pizza. It might not come, but yeah, thank you so much for playing with the demo. So now, what is Serverless? So Serverless, it's very hard. It's very hard to define, and everyone has his own definition of Serverless. So I won't be more clever than everyone, so I'll stick with what AWS and GCP are telling about Serverless. But yeah, both are mainly the same. It's focused on the fact that you're not focusing on the architecture, but more about building stuff. So it's a great developer experience, at least for me, and I'm sure if you're not using Serverless and you want to try it, I'm sure you will be amazed by the developer experience that it provides. So 4 main things about Serverless. You deploy code only and not infra. So we will see in a moment that when you deploy components such as a Lambda function, which react to events, you don't need to bring your own server. You don't need to bring your own API gateway. AWS has something for you, which is fully serverless. So you really focus on the business logic and not about the aspect of keeping your server up to date, managing certificates, and so on. AWS or other cloud providers such as GCP as well have a serverless solution, so you can really focus on your code. Another cool aspect is it's automatically scaling. So if you have let's say a pizza shop, and maybe on Monday it's closed, you don't want to pay for your servers on Monday because obviously there won't be any orders on Monday because you're closed. But maybe on Tuesday around midday, a big spike of traffic, a lot of pizza will be delivered, and now you need to spawn a lot of different servers. And this can be difficult in a non-serverless world. But For serverless, it's built in. You don't have to do anything. It will scale for you. If you use it correctly, you have a built-in high availability. So it means that if you deploy a new version, the traffic will spawn, will change from the V1 to V2. You have to do some best practice in the code, but it's generally built-in. And the fourth and not the least is pay as you use. So it's usually built by milliseconds. So the faster your function will be, or your container will spawn, the lower the price will be at the end of the month. So this is a big 4 of serverless. Of course, there's more features, but let's focus on that today. So you may already know serverless. We talked about AWS Lambda. We are going to talk about Cloud Run as well from Google, but it's way more than that. There are DynamoDB, S3. There are a lot of different serverless services, but yeah, today we are going to focus on AWS Lambda and Google Cloud Run. So let's start by AWS function. You can see that as a function as a service. So you deploy only a function and it will become a service. It will be event driven. So it will wake up by an event. It can be a HTTP gateway event. It can be a WebSocket message, just as we just saw. It can be when you put an object into a S3 bucket, it can wake up a Lambda function. And it's supporting almost any language. Out of the box, we have Ruby, Java, Go, Node, Python, and so on. And of course, we can bring your own runtime. And guess what? We are at the Rust meetup. We are going to talk about Rust. So as I said before, since it's not always on, if you don't have any traffic, your Lambda function won't be up. You have what we call a cold start. It means that the first request, or when you have a big spike of requests and your current instance cannot keep up to the pace of the incoming request, another Lambda function will spawn, another sandbox, and this is what we call a cold start. And the cold start is actually free. You don't pay for that, but you pay in terms of latency, because if your function is taking 5 seconds to start, well, someone at some point will wait for 5 seconds. And as you saw, I hope, actually, during the demo, there was no latency. Everything was super smooth. And we switch from, obviously, we are maybe, I don't know, 30 to 100. It's not big spike of traffic. But the point is, if we had like 1,000 orders, the website would have been super responsive as well. Trust me on that. So since the function is not always on, we have what we call a cold start and a warm start. So both are starting with an event because AWS Lambda function is taking an event. So let's say it's a WebSocket event or an API gateway event, HTTP request, for instance. So AWS will first download the code, start the environment. Underneath, it's a Firecracker VM. And then we have code initialization. So the yellow thing are for a cold start. And then finally, your function will execute. Let's say it's, I don't know, hello world, or put a pizza into a DynamoDB. So this will execute your code. On the second request, or when you have more traffic, every other request than a cold start will be a warm start. So we don't need to download the code. We don't need to start the environment because it's already there and the code has been already initialized. So then you just execute your code. So yeah, so this is a warm start and a cold start. And of course, if we want to have a lowest latency possible, latency, you need to make sure that, for instance, code initialization is really, really small. So I've developed a small tool, which is Lambda Perf. I don't know if you already seen that before, but it's an always up-to-date benchmark of cold start over every runtime. So I'm going to zoom a bit. I don't know how big the screen will be, but each yellow spot is one cold start. So if I refresh, in real time, you see what does it take to wake up 10 Lambda function written in Rust, in Python, in Ruby, in Node.js, in Java. And it's always up to date because it's auto-updating every day. Every day, every single Lambda function will be destroyed, will be recreated, and we invoke 10 times, making sure it's a cold start. We take the average duration, and this will be printed out on this website. And as you can see, Rust is the fastest, actually. And we are going to see why. And we are going to see why Rust is such a great candidate for serverless. If you care about latency, of course, if you're doing some asynchronous job and where latency does not really matter, maybe Rust is not the best option. But let's say we want to have a very low latency system. So yeah, if you want to see how does it work, it's fully open source on GitHub. If you want to contribute to a new runtimes, feel free. The aim is to have like a very open project. It's not biased in any way. It's just a hello world in every runtime. So yeah, Rust is winning for that. So yeah, download the code. There is nothing you can really do about that. I guess your Lambda function, it will not be like 1 gigabyte. So AWS has some internal mechanism to cache your dependency and so on. So should be really, really fast to download. This is a guess. It's not officially documented, but I guess there is some good optimization. Start the environment. Once again, you can do really something about that. A Firecracker VM will spawn. It's Node.js Go. It's the exact same underlying infra. But then you have code initialization. And this is where Rust could play a huge role. And this is what we saw in the benchmark. If you're using Rust, the code initialization will be faster. Let's see why. So yeah, I spoiled it, but let's talk about Rust for that, because we saw that Rust was best candidate for that. So why Rust has faster cold start? First, Rust binary can be extremely small. As you may know, there is no garbage collection in Rust. So the runtime footprint, the minimal code to run a Rust binary is extremely small, and it's hard to beat. For instance, I have nothing against Go once again, but if you start with a hello world with Go, there is a Go runtime inside this binary. So the binary will be a bit bigger, and we'll see some numbers a bit later. But Rust, there is no garbage collection, so the memory, the size of the binary is extremely small. And if it's small, it takes less amount of time to load into memory, and it's faster to start. The other thing is that Rust is extremely good at memory management. So you can have very tight control on number of allocation, size of the allocation, and so on. Because of course, if you're doing a lot of allocation on the heap, on the stack, the time to start the binary will be longer. So Rust is really nice candidate for that, because you can have control on that. Rust has also some very interesting building flag. So let's say you have your Lambda function written in Rust. What we can do is we can play with build flags, to make sure that the binary is extremely small and really well optimized. So the first flag is the optimization level. If you set it to Z, it means it's optimized for size. So maybe not for performance when it runs, but the binary will be extremely small, and it means that it will be fast to run. So the cold start will be extremely fast. Maybe the runtime duration will be a bit slower if you optimize for size and not performance, but that's a trade-off. So you can play with that and see how it affects cold starts. Second flag is LTO, means linked time optimization. So if you enable it, the optimization overall will be a bit better, but at the cost of a longer linking time. So if you're not in a hurry, it's really, for a hello world, it's a couple of milliseconds. Maybe for a bigger application, might be a bit different. But for serverless, once again, I strongly suggest you to try this flag. Then you have the code generation unit. By default, Rust is doing some local optimization of the code for each unit. So let's say you have 10 units of compilation. You will have a local optimization in each one of those 10 blocks. But it tends to be faster to compile. But of course, if an optimization can be done within 2 blocks, it won't be done. So if you specify that you only want to have one code generation unit, you are sure that all the local optimization will be done at the same place. Then you will have a faster binary. At a longer compile time, once again, but sometimes that's fine. And the last flag, I'm sure you already know what is a panic in Rust. You have this nice stack trace, which is really useful to debug. But for a Lambda function, maybe you don't need that. So you can strip it, and instead of outputting the full stack trace, you just abort, and that's it. So it will remove the code used to unwind the error up to the very top of the stack trace. If you don't need that, you can strip it. So this is for the bit flags. So show me numbers now. For Rust Hello World Lambda function, the size with the 4 flags I've just shown is about 722 kilobytes. So extremely small. For instance, once again, nothing against Go. I need to take another runtime for reference. So Go is 4.7. So maybe there's some flag that I didn't use, but I use W and S to strip the symbol table and so on to try to have like as small as possible. But yeah, this is a no-brainer. It's almost 5 times smaller. So yeah, that's it for Lambda. And now I want to show you something. So for the connection, this is a Lambda function written in Node.js. And this is when someone is going to the website, it will receive a connection event from the WebSocket saying, I want to order pizza. So what we need to do to keep track of that is to insert something in DynamoDB, which is a table available, not a table, or like a database system from AWS. And what we want to do is to match the current ID of the connection to the order ID that we want to track. So if we go back here, for instance, here I have an ID. So if I change the status, then I can match the current connection to the current order ID to update the UI. So what I need to do is to read the events. So once again, Lambda is working with events, incoming events. So I read the events, I check the query string, I check if there is an order ID, then I put an item into DynamoDB. And if we want to have a look, so there's no one on the website currently. If I refresh, if I go back to my website, I should have an item here. Yes. So as you can see, it's fully real time. Nothing is hard-coded. So we have a connection ID. I say that it's connected, and then we have the order ID. So that's fine. If we look at the log connection, we can see that this function, the init duration, so the cold start duration, is about, I can zoom a bit if you want, is about 294 milliseconds. So it's pretty good. It's quite fast. But if we want to go a bit further, maybe we can rewrite it to Rust. And I'm going to show you the code in a moment. And in Rust, it's doing the exact same stuff. I will show you the code in a moment. And if you look at the report log line, the init duration is now 43 milliseconds. So of course, we saw with Hello World that Rust is beating Go, for instance. But as soon as we have a bigger use case, such as, it's not super big, but it's like taking an event, reading the query string parameter, and put an item in DynamoDB. For all of that, in terms of init duration, so loading the AWS SDK into memory and so on, we only take 43 milliseconds, which is, to me, like mind-blowing. It's super fast. And then the actual runtime, it's 99 to actually put an item, 99 against 572. So once again, the runtime duration is quite faster with Rust as well. So now I want to show you a bit of code. So I have a code here. It's a Rust code to deploy and to build the Lambda function. So the first main function is actually receiving an event. So once again, it's in a WebSocket proxy request. So these events are provided by AWS. So you just need to import the library, and we will have the proxy request. Then what we need to do, instead of hard coding the table name, you can read it for the environment variable, for instance. Then I take the order ID. Finally, I spawn a new DynamoDB client. I put an item, and that's it. So this is the exact same code that I've shown you in Node.js, but written in Rust. First, it's super fun to write, super easy to test as well, and super easy to deploy like any other runtimes. But yeah, so the code will be available open source if you want to have a look. But yeah, that's it for Rust Lambda function. Really simple. just have a main. If you want to have a tracing, of course, that's always better. Put an item into DynamoDB, and that's it. And as you can see, the runtime goes from, the init duration goes from more than 200 milliseconds to below 50 milliseconds, which is pretty neat. So yeah, serverless is obviously not just Lambda. We have other stuff as well. So let's have a look at Cloud Run, for instance. So Cloud Run is a service from GCP, Google Cloud Platform, which you can see that as a Lambda function, but maybe a bit bigger. Let's say instead of having just one entry point, which is your Lambda function, you can have a full container. So let's say you want to have like a Express server in Node.js or Actix web server in Rust. So it's really like a container, no constraints, no runtime API, no nothing. It's just a regular container. You ship it to Cloud Run, and it will auto-scale depending on your need, and it can scale to 0. And once again, if it can scale to 0, it means that you are going to experience a cold start as well. So I have done a small experiment that I'm going to show you. Here I have Cloud Run. So for instance, I have a Go container. So as you can see, very simple Go. I will listen and serve port 8080, and I will return hello from Go. I have the exact same stuff for Node.js. So hello from Node.js, just using Express. And for Rust as well. For Rust, I created a test to show you how a big enthusiast I am about Rust. But you should write test for everything, of course. But yeah, so you have an Actix web service, just spawn a hello root and hello from Rust. Very simple code, and I have deployed it here. So if we go to the Go, I will zoom it. It will say hello from Go, hello from Rust, and hello from Node.js. So the exact same cloud container for 3 different runtimes. Now let's add a benchmark of that. So I prepared a dashboard for you. This dashboard is directly available on the Google Cloud console. So no instrumentation library, which could impact cold start, no nothing, just plain metrics. So let me zoom a bit. First, I will show you what I've done. I load test the 3 services. So sending a lot of requests, as you can see, a lot. It's not huge, but 150 requests per second. It's enough to spawn new containers continuously, because one container cannot handle that much load. So as you can see, each color is one runtime. So Go, Node, and Rust. And obviously, not to cheat, I send the exact same number of requests to both 3 runtimes. First things to note is the request latency. So once the container is warm, we can check how long the hello world is taking. And Go and Rust are almost the same, about 1.6 milliseconds. And I'm not sure why, but Node.js is a bit longer, but yeah, 1 millisecond, maybe that's fine. Just to print hello world, that's not a big deal. If you look at the 99th percentile, so let's say outliers, the longest request, Rust is winning as well, about half a millisecond. So I'm not sure this is really interesting, but yeah, just to show you the request latency, that's no big deal. What is really interesting is the container startup latency. So once the container is full of requests, we need to spawn a new one because otherwise you are going to wait too long. So the fact of spawning a new container, of course, you need to download the image. And in this test, I use the exact same image for the 3. It's a distroless Node.js and Debian-based image. The code will be available if you want to reproduce that at home. And as you can see, to spawn a new Rust container is about 119 milliseconds, which is once again absolutely mind-blowing. Go takes a bit longer, 144, but still okay. But as soon as you're hitting like non-compiled language, it takes longer. So maybe a bit more than half a second for Node.js. And if we look at the, yeah, this is, should have done that, but yeah, you get the point. 50 percentile and 99, and Rust is still winning. So the point is, like, when you need to scale out to handle more traffic, you need to first ask yourself, do I need this to be extremely fast? Or maybe it's a night job and I don't really care about that. But if you really need, if it's like client facing, maybe you need it to be really, really performant, and maybe Rust could be a good option here. So yeah, Cloud Run, container as a service, auto-scaling, as I just mentioned, experiencing a cold start as well when the container is full of requests. Then you need to spawn a new one, and this takes time, and you need to be really careful about which runtime you want to use. Just did the demo, and yeah, that's it for me. I hope I convinced you to at least have a look at Rust for serverless if you actually need it. But yeah, I could not emphasize how fun it is to write Rust for serverless. A great tooling. I mentioned AWS Lambda. AWS is doing a really great job for the SDK of writing Rust Lambda function. So it's really, really fun. Every incoming event are already supported. So DynamoDB, WebSocket, S3, a lot of different examples are available on the GitHub. So yeah,